Assalamu alaikum jami'an. Good morning, everyone. It's really good to see you. Well, not to see you, but to be with you again on the second semester. I have uploaded all my lectures to Moodle. I uploaded them half an hour ago or maybe 40 minutes ago. So you'll have all lectures, 9 lectures for the amino acids portion and the first 3 lectures of the carbohydrates section, which I'll be covering as well with you. So I hope you got the chance to at least maybe download the first lecture, which we will discuss today. So yes, so this is what's gonna happen for the next 3 weeks. I'm gonna see you every Monday, Tuesday, Wednesday from 8:30 to 9:20, and then we will have a tutorial on Sunday. So more or less exactly the same thing as biology. As always, you're more than welcome to email me any questions, any queries. And if not, you also have another opportunity, which is during the tutorial for almost 1 hour, which, we will, review the things or the lectures, the concepts that we discussed the week before. And if after the tutorial you have doubts, then feel free to email me again and I can help you via email or via Zoom. So I'll be more than happy to arrange a Zoom meeting with anyone if there's a particular issue that they are facing with respect to understanding some concepts or the lecture. And yeah, so as always, I like to be interactive, but the way, as you know, these lectures are designed, sometimes we may be pressed for time. So you can send a message via the chat, but I do apologize in advance if I'm unable to answer you right away. I'll do my best though. I promise I'll do my best that as I'm explaining, I'll have a look at the chat. If not, towards the end, I can just dedicate a few minutes to answer your questions. Okay, so then now you might ask me, this course or this section or this block is about amino acids. Why are you explaining matter and all these things? So the purpose of this lecture in particular is to kind of go over some basic concepts that you're all probably very familiar with, and you might even, you've taken it recently, maybe even much more in depth during your high school studies. But the idea is to cover these basics because we will discuss them when we start our discussions about amino acids. So for us to understand, for example, how proteins are formed, they're basically formed by merging of amino acids together. So then how are these combined together? How are these amino acids combined together? They're combined together by certain chemical bonds. So it makes sense that we need to understand what are the different types of chemical bonds. And for us to understand that, we need to kind of understand what are atoms? Why do they like to sometimes form covalent bonds or ionic bonds? What is the octet rule? And so on. So now it's like, think of it as an introduction type of lecture about key concepts that will matter once we talk about the structure of amino acids, how proteins are formed, the properties of amino acids, etc. So a matter is really anything that occupies a space. So this could be it could be in the form of solid, it could be in the form of gas, it could be in the form of liquid. It really, as long as it occupies space, then this will be you can call that a matter. And any matter, anything that occupies space, is composed of elements. So we have really many different elements. I'm sure you're all familiar with the periodic table of elements, but there are certain elements that are particularly very common in living things, in the body, in cells, in DNA, in protein. And this is essentially hydrogen, carbon, nitrogen, oxygen, phosphorus, and sulfur. So these are typically, you'll find them in like carbohydrates and lipids and amino acids and proteins and DNA. So this is essentially what you would commonly find in living things. And these elements are composed of atoms, ذرة. And the atoms are composed of subatomic particles like neutrons and protons and electrons. So the protons and neutrons are found in the nucleus, whereas the electrons are found surrounding the nucleus, where they occupy certain the shells, the electronic shells that surround that nucleus. So this is what the periodic table of chemical elements, which you're all familiar with. It's just there to give you an idea that there's so many different elements, that they have so many different properties, and based on their atomic number, their properties, etc., they have compiled them and grouped them into this periodic table of elements. We are not required to know details about this. I'm sure you've learned enough about it in high school. This is really not the purpose of this lecture. Just to let you know that we have a lot of elements, but then we are interested in particular in certain elements that are very common in living things, because when we talk about structure of amino acid, or we talk about the structure of carbohydrates and so on, you'll realize that there are certain elements. There is a common, basically, let's say, I wouldn't say common chemical formula, but there are certain elements that we'll always see in these living things, which we will discuss greatly in this course, this biochemistry course. So back to our elements, which are composed of atoms. They have these subatomic particles like protons, neutrons, and electrons. And I would really appreciate if you would have an idea about these definitions. So protons are positively charged particles with a mass of 1 AMU, or atomic mass unit. So that is what a proton is. It is positively charged, found in the nucleus. Neutrons, also found in the nucleus, have no net charge, so they have no charge. And they also have, similar to protons, a mass of 1 AMU. And similar to protons, they are also found in the nucleus. Electrons, on the other hand, are negatively charged. They are not found in the nucleus, and they are much smaller. So they are approximately 1/1800 AMU. And their arrangement is determined by total number of electrons and electron shells that they occupy. So these electrons that are found in these shells, they will arrange themselves in a certain way. So you have like the closest shell to the nucleus, as you will see in the next slide. It is the K shell. The maximum electrons it can occupy is 2. And then subsequent shells can have more than that. And they distribute themselves on these shells. Positrons are not really relevant to us in terms of elements or atoms. I'm just mentioning them because they are similar to electrons in mass, like they are small, they are the counterpart of electrons, but instead of being negatively charged, they are positively charged. So they do also have a negligible mass, a very small mass, but they are positively charged. They are not found in the nucleus nor in these electron shells. They may be relevant more in like when it comes to like cosmic rays cosmic rays essentially. So these are the definitions. That's what you just have to have an idea of. I'm sure you're familiar with these. Just remember which is negatively charged, which is positively charged, and then, like, for example, which one in the nucleus and which one are in the shells, outer shells. So this is essentially what I said. This is the structure of some elements like hydrogen. It's composed of like this nucleus. It has 1 proton, no neutrons, and then 1 electron and the closest, the K shell. And then carbon, it has 6 protons, 6 neutrons, 6 electrons, of course. And this is the organization of the electrons on the shells. So the first shell, there's two electrons, and then the second shell, the L shell, has four, and the list goes on. So just to give you an idea, once again, I know that you already are very familiar with this, and you've probably studied this in much greater detail. With respect to energy, what is energy? Now, the energy is the ability to do work, and electrons that are found in these electron shells around the nucleus, they are constantly moving. Therefore, their ability to move makes them possess this energy. So they have energy. And the further the electron away, and the further that electron is away from the nucleus, the more energy it possesses. Therefore, the electrons with the least amount of potential energy are found in the K shell, or the first shell, or the shell. This is K, K, L, M, N, O, and so on. So the first shell, the closest shell to the nucleus, it possesses a maximum of 2 electrons, and usually these electrons have the least amount of energy. That also means that these electrons are the least likely electrons to be involved in reactions or chemical bond formation. But the outermost electrons, these are the ones that possess the most energy. They're unstable. They're the ones that are likely to be involved in chemical reactions. And the thing about these electrons or these atoms is that it likes to have a full outer shell. So it likes to be more stable and have the electron configuration that is seen in noble gases. And that is when the octet rule applies. What does this rule state? It states that elements, they will gain or lose or share electrons to attain an electron configuration of the nearest noble gas. So this is basically what the octet rule implies. And yes, and that's basically how they do it. It could be through giving up electrons or gaining electrons. Like this happens when you form ionic bonds, for example. One atom loses electrons and the other one gains it. Or they can be sharing electrons like you would see in a covalent bond. Regardless, the goal is to have a stable outer shell, a full outer shell that will have 8 electrons that will resemble the electron configuration of noble gases. All right, so that is just like some brief introduction. Now we know that we have all these elements, but then we also realize that only few elements are relevant to us in the field of biochemistry and in the proteins, the DNA, the things that form our bodies, that are found in our cells. We know what atoms are, we know what are the subatomic particles, and we now know that electrons, possess energy, and the further an electron is from the nucleus, the more energy it possesses, whereas those that are closest to the nucleus in the K shell, these possess the least amount of energy. And we described the octet rule, which is when the element gains or loses or shares electrons to reach the electron configuration of noble gases. Now, another definition is molecules. So molecules are electrically neutral group of 2 or more atoms. So it could be an oxygen molecule. So that is 2 oxygen atoms that are bound together by means of a covalent bond in this case, to form they form these very strong chemical bonds to give us O2, what we know as the oxygen molecule. So that oxygen molecule is composed of 2 atoms. Sometimes you may have molecules that are actually composed of different atoms, in which case we can call them compounds. And an example is water compound. It's a form of molecule. It's just that instead of having the same two of the same elements or atoms, you will have a combination of different atoms. And we have many other molecules or compounds that exist. It could be acid, it could be base, it could be water, really, essentially, it could be anything. Electrons possess energy, therefore bonds exist between atoms and molecules. And these bonds contain energy. And you will see that when you break a chemical bond, for example, break a covalent bond, you essentially release energy. But when you want to form that bond, you need energy to form that bond. And we'll see this later in tomorrow's lecture when we talk about chemical reactions. So this is an example of a water molecule, which is really a compound. So it is a compound composed of 2 hydrogen atoms and 1 oxygen atom. Now, oxygen has 8 electrons. 2 of them are in the K shell, whereas 6 of them are distributed in the outermost shell or the second shell or the L shell. So 1, 2, 3, 4, 5, 6. There's 6, but atoms in general like to engage, as we said, they like to share electrons or they like to gain or lose to reach the electron configuration of a noble gas, to have 8 electrons in the outermost shell. That is the octet rule. Octet means 8. So what it does is that it shares electrons with 2 hydrogen atoms. Hydrogen only has 1 electron that is in the K shell. So by doing this, they all benefit from each other. Hydrogen will now have 2 electrons in its shell. So that is the fuller shell for the K. That's the maximum capacity the K shell can have. And the other hydrogen, you'll have 2. So let's assume 1, for example, belongs to this hydrogen because hydrogen has 1 proton and 1 electron. And the other one is shared. It's what it is sharing with the oxygen. Same thing with the other hydrogen atom here. So now this hydrogen has 2, and this hydrogen has 2, and this oxygen has 8 in the outer shell. And now you have the water molecule, and you have a stable molecule. So let's talk about chemical bonds. How is this sharing happening? Sharing of electrons is basically what happens in covalent bonds. So let's talk a little bit about chemical bonds. Generally speaking, chemical bonds can be divided into covalent bonds and non-covalent bonds. The most stable type of bonds, the strongest form of bonds, are actually the covalent bonds, whereas the non-covalent bonds are less strong, and we have different types. This includes ionic bonds, which are relatively strong, but then there are other non-covalent bonds that I will discuss with you in detail in the next slide. So let's talk a little bit about covalent bonds. These are also called primary bonds. They form when atoms share electrons. These are known the valence electrons, or the electrons that will be shared. They're there in the outermost shell. Okay, and the outermost shell is sometimes also known as the valence shell, excuse me. So by doing this, by sharing these valence electrons that are found in the valence outermost shell, these atoms will have they will have a full shell and they'll become stable. And this is a very strong type of bond. And this is essentially the type of bond that will form the backbone of DNA. Remember when we were talking about DNA, when we talk about phosphodiester bonds, these are a type of covalent bonds. They're very strong. Same thing if you want something relevant to what we're going to be discussing in this block of this course is peptide bond. So peptide bond is a bond between 2 amino acids. And these peptide bonds are very strong and they are a form of covalent bond. And the most common covalent bonds, you'll notice they're in biological molecules are between carbon. So you'll see a carbon and a carbon, or a carbon and a hydrogen, or it could be a carbon and an oxygen, or a water molecule, for example. So all these are a form of covalent bonds. These are all examples: water, methane, carbon dioxide, carbon molecule, or carbon and hydrogen, like this hydrocarbon compounds. So these are what we mean by covalent bonds. Now I'm going to take you to some different types of other types of bonds that are weaker. These could be between ions, or they could be between parts of molecules, and they are weaker than covalent bonds. So we refer to them as non-covalent bonds. So this includes hydrogen bonds, ionic bonds, hydrophobic interactions, and van der Waals forces. So let's take these step by step or one by one. So what are hydrogen bonds? These are attractive interactions. So we say interaction because it's not real. There's no sharing of electrons. There's no movement and donation of electrons and gaining of electrons. It's just interaction that happens between hydrogen and an electronegative atom. This electronegative atom could be a nitrogen, most commonly either nitrogen or oxygen. Sometimes it could be fluorine. So because the name, there's hydrogen in the name, there's hydrogen in the title, so it has to be hydrogen, an interaction with hydrogen, and something else. Hydrogen is electropositive, therefore it interacts with electronegative atoms like oxygen and nitrogen. And these hydrogen bonds are found in water, but not to form a water molecule, because we already know that a water molecule is composed of covalent bonds. But that actually happens between water molecules. So if you have this is one water molecule composed of two oxygen atoms shown in white and two hydrogen atoms shown in white and one oxygen atom in the middle shown in red. So this is one molecule composed of two hydrogens and one oxygen, and they form this molecule by a means of covalent bond. But what happens when you have water, you have a lot of molecules of water that are next to each other. So what happens between these water molecules? There are attractive forces that brings them together, that gives a lot of the features of water that they're known of. So if you have one water molecule here, another one nearby here, another one here, here, what happens is between two water molecules, for example, there will be some attractive forces. Why? This oxygen, even though in this molecule it is neutral, because now it's a molecule, it is neutral, but that oxygen will still have a partially negative charge. Think of it this way. When it is interacting with hydrogen, and it's forming this covalent bond, it is sharing that electron. The electrons spend slightly more time with the oxygen compared to the hydrogen. And that will always make, even though water molecule is a neutral molecule, the oxygen part of that molecule is partially negative, whereas the hydrogen part is partially positive. Therefore, the hydrogen here from one molecule will have some attractive forces with this oxygen from a neighboring water molecule that is partially electronegative. So you can technically, if you look at one molecule, it'll have these multiple interactions, these hydrogen bonds with neighboring water molecules. And that is what hydrogen bond essentially is. So not only can it be between molecules, like intramolecular, between different parts of a molecule, but it can actually be between two different molecules, so intermolecular. And the best example would be DNA, because that's something that we already discussed with you. So remember when we talked about the two strands of the DNA, and we said that those two strands are bound together, linked together by means of hydrogen bonds, and that these hydrogen bonds occur between nitrogenous bases. So that is what base pairing is. So you have A base pairs with T, C base pairs with G, and we said A-T base pairing requires two hydrogen bonds, whereas base pairing between C and G is 3 hydrogen bonds. So these are hydrogen bonds. There's always a hydrogen involved from one nitrogenous base, and on the other, it'll be an electronegative molecule. And in the case of DNA, it is either nitrogen or oxygen. And they have these attractive forces. So these are hydrogen bonds. They are stronger than other forms of non-covalent bonds like van der Waals forces, but they are weaker than covalent bonds or ionic bonds. So ionic bonds from these list of non-covalent bonds are actually the strongest. So let's take a moment to talk about ionic bonds. These are formed by the attraction between two oppositely charged ions, and it's usually a metal and a non-metal. فلز مع لا فلز. So the metal donates one or more electron to have a stable electron configuration and becomes positively charged. That'll be the cation. And the other one will, the non-metal will gain an electron, so it'll become negatively charged. That is called an anion. So this is basically what happens. It's when there's attractive forces between a cation and an anion, there'll be one will donate, one will gain an electron, and that will form your ionic bond. So bonds between oppositely charged ions, a metal and a non-metal, an anion and a cation and an anion, will form ionic bonds. And the examples here, sodium chloride, calcium chloride, potassium chloride. It is always a metal like sodium or calcium or potassium with a non-metal, like in this case, chloride. Positively charged with negatively charged. So these are ionic bonds, and these are stronger than hydrogen bonds, but not as strong as covalent bonds. Hydrophobic interactions are basically, they usually happen between nonpolar molecules. Nonpolar meaning hydrophobic. That's another way of saying hydrophobic. They are not water soluble. They don't like water. They are hydrophobic. They are non-polar. And what happens is that these molecules, if they have this feature, the feature meaning they don't like water, they tend to aggregate with each other. And this will make sense, especially when we talk about, for example, how proteins are folded. Proteins, we will take this step by step. You'll come to realize that amino acids can be broadly classified into polar and non-polar. And when you synthesize a protein, which is composed of a long chain of amino acids, that protein will have some polar amino acids and some non-polar amino acids. It's a combination of amino acids. And what happens is that during protein folding, the protein likes to fold in a way so that all the polar amino acids, they aggregate with each other in the center and the core, whereas the non-polar, those that love water, will stay on the surface. And that makes sense because protein is usually found in aqueous environment, has water. So those water-loving amino acids will remain on the surface, whereas those hydrophobic amino acids will go in the center. Okay, so that gives them, there is this drive for these hydrophobic units to form these hydrophobic pockets to stabilize the structure of a protein, so that these are hydrophobic forces or hydrophobic interactions. And last is the van der Waals forces. These are relatively weak, and these forces occur and they are dependent on the relative orientation of a molecule. What that means is, if you have this molecule here, it's in space, sitting, minding its own business, as the electrons, I mean, it is composed of electrons, right, that are found in the shells, and they are constantly moving. At certain times, while these electrons are moving, at certain times, you may have more electrons here. They're all aggregated in this for whatever reason. They're just simply found in this orientation. So that will cause momentarily something called a dipole. That molecule will kind of have an area that is negatively charged and an area that is kind of relatively partially charged, simply because the electrons happen to be, as they are spinning around, they just happen to be all on one side, whereas the other ones is having much less electrons. So this is dynamic, this is changing, it's constantly changing. So as this happens, these molecules of opposite charge will come closer together. They'll have these forces, attractive forces. But remember, this constantly changes. So one moment this molecule might be attracted here, the next moment might go here, and so on. So it really has to do with that point of time and point in time and space where you will have this momentary charge. But it makes you understand that that molecule can be a dipole, can have this partial charges that, depending on these charges, they may be attracted to other molecules nearby in the vicinity of the opposite charge. So this is in a nutshell what non-covalent bonds are. So we talked about atoms and elements and subatomic particles, and we talked about, electrons, how they like to, how these atoms follow the octet rule, how they share or donate electrons or gain electrons to be more stable, to form molecules, to form compounds. Now let's talk about something else, which are solutions. Just some definitions. What are solutions? There are two types of solutions, crystalloid and colloid. So crystalloid solutions are basically composed of crystallizable substances like sugar or salt that once dissolved in water, they dissolve completely, and because they dissolve completely, that solution, that crystalloid solution, will diffuse readily through a semi-permeable membrane, whereas a colloid solution is just like a mixture of larger molecules. It's not salt, it is not a crystallizable substance, it is not sugar, it does not dissolve really, but you can mix it, and it will always have these small, teeny tiny particles that will disperse through that water. And because it never really dissolves, therefore it does not diffuse through semi-permeable membrane. So just some definitions. Now I'd like to take a moment to skip to the next part, which is water. I'll talk a little bit. We talked about the structure of water. We said that a single water molecule is composed of 2 hydrogen, 1 oxygen, bound together by covalent bonds. And we also said each neighboring water molecules, they will interact with each other by non-covalent bond, which is the hydrogen bond. Now let's talk a little bit about some features of water, because as you know, water is very important for many things, but Also remember that our body is composed largely of water. So water is essentially a neutral molecule. It is a stable molecule. So when you have like a bucket of water, it is stable, it stays as it is neutral. However, a very small fraction of that water does ionize. So it does dissociate into hydronium and hydroxide. For simplicity, we can write the formula in this way, meaning hydrogen instead of hydronium and hydroxide. So we write it this way for simplicity purposes. So water ionizes partially, very small fraction of water ionizes. The majority, 99 point something percent, will remain in this state, but it still partially ionizes into hydrogen and hydroxide. And because this goes two-way, it just gives you an idea that this can change based on different basically things, but it happens actually at a constant rate. So this is known as the equilibrium constant of water, meaning that process, that ionization that I spoke of, that auto-ionization that happens to a small fraction of water actually happens at a constant rate, and it's known as Kw, or the equilibrium constant of water, or the ion product constant of water. And this constant means doesn't change, at 25 degrees Celsius is equivalent to 1 times 10 to the power of minus 14 molar square, or square molar. So Kw is equivalent to the concentration of hydrogen multiplied by the concentration of oxygen. So if the concentrations of hydrogen and hydroxide, you multiply them together, it'll always give you, if the water is at 25 degrees Celsius, it'll always give you this number. Now, this means that in a way, if you increase hydrogen, this will drop, and vice versa, because the constant has to stay the same. You can't increase both of them, because if you increase both of them, this will change. So that makes sense. Okay, so this is basically what we mean by ionization of water. So does water ionize? Yes, very small portion of water ionizes, and it happens at a constant rate. And because it happens at a constant rate, we were able to calculate something known as Kw. Kw, which is the equilibrium constant of water, is equivalent to hydrogen ion concentration multiplied by hydroxide ion concentration, and it is always equivalent to this. Why am I teaching you this? Why are we saying this? So this is just a visual representation of what I just explained. So this, if you have a glass full of water, a very small amount of this water will ionize into hydrogen and hydroxide. Okay, and usually under normal circumstances, those two, when you multiply them with each other, it'll always give this constant number, this Kw number, 1 times 10 to the power of minus 14. So if hydrogen is equivalent, the concentration of hydrogen is the same as the concentration of hydroxide, it means that each one of them will have a concentration of 1 times 10 to the power of minus 7. But if hydrogen increases, the other one you expect it to decrease, and vice versa, okay, for this to remain the same. And in this case, the water will have more hydrogen. So you expect, because if you want this to stay the same, this means that if you have more hydrogen, you'll have less hydroxide. And this is, we can say that this water is slightly acidic because it has more hydrogen, and vice versa. If the water is slightly more basic, then you'll have more hydroxide. But at the end of the day, multiplying them will remain somewhat constant. why are we saying all of this? Why are we talking about this ionization of water and that it happens at a constant rate and it is equivalent to 1 times 10 to the power of minus 14? But remember, this is at normal conditions at 25 degrees Celsius, because water, actually, I don't want to complicate things, so I'll just say this, but forget it, Yanni. At different temperatures, it'll have different pH. Anyways, why are we explaining all of this? Because this feature of water helps us come up with a scale, a very important scale that helps us to measure the acidity, or how acidic or how alkaline a solution is, and that is known as pH. We say a solution is neutral when hydrogen ion concentration is equivalent to hydroxide ion concentration, and it is equivalent to 1 times 10 to the power of minus 7 molar. So if you know hydrogen ion concentration, you will know the pH of a solution, because pH is equal to the minus log of hydrogen ion concentration, or log 1 over hydrogen ion concentration. So for neutral solution, it'll be 7. Okay, the log of this is basically 7 minus log. So if a solution is neutral, is 7. If a solution is acidic, because again, it's minus log hydrogen ion concentration. So if the hydrogen ion concentration is high, the pH would be higher or lower? Would be lower. And vice versa, if hydrogen ion concentration is low, when you take the minus log, it'll be a larger number. So that is a basic solution. Therefore, technically, 7 is neutral. Anything less than that is considered acidic. Anything more than that is considered basic. In our body, we have the physiological pH ranges between 6.5 to 8. The blood is like 7.4, but then you have different compartments that will have either slightly more alkaline or acidic environment. And shown in front of you is how these the pH in our body in different compartments can vary greatly. Like the gastric juices, which has very strong acid, HCl, can have a pH of close to 1. That is very acidic. Lysosomes, it's like 4.5. Urine, slightly acidic. Cytosol is more or less neutral. Same thing for the CSF. Same thing for blood. The pH range is between 7.3 4 to 7.45, and it's very important for us to keep the blood in that range. Otherwise, if it becomes more acidic, you'll have something called acidosis. If it's too basic, you'll have a medical condition called alkalosis. But luckily, our body has ways to prevent that from happening. But nonetheless, it still happens in certain disease conditions. So now we talked about one important feature of water, and that it ionizes, and that ionization, it is very gradual, very small fraction of it ionizes. But from that, knowing the constant of this ionization of water, which is equivalent at 25 degrees to 1 times 10 to the power of minus 14, we were able to calculate something called pH. And we said the pH is minus log hydrogen ion concentration. Now let's take a moment to talk about ionization of acids and bases. Because this is going to be basically very important for you to understand something called, just like I told you, for example, our blood has a certain pH, and we don't want it to shift from that range, that physiological range. Luckily, we have buffers in our bodies that buffer and that resist changes in pH. If some acid products or somehow they get into the bloodstream, it doesn't immediately cause acidosis because we can buffer. But to a certain extent, sometimes we lose that buffering capacity. There's only so much that we can do. But for us to understand these buffer systems in our bodies, let's talk about a little bit about ionization of acids and bases, and that will help you understand the buffers, because buffers are generally a combination of weak acids and their conjugate base. Step by step, you'll know what I'm trying to get to. So acids, weak acids and bases are commonly found in our bodies, and these partially ionize in, the physiological pH. And for simplicity, we're going to focus on weak acids. So if you have a weak acid, we'll put a general formula, H, because it's an acid, and A, randomly. It could be citric acid, acetic acid, it could be any weak acid. So this in an aqueous solution, in the body, for example, in the presence of water, naturally it ionizes into hydrogen ion and the conjugate base. And this happens at a constant rate, just like water ionizes at a constant rate, and we were able to measure that. Also, weak acids and other acids will ionize in solution at a constant rate. And that rate is different for each acid. Each acid has this unique number, that unique constant. And this is for acids known as the dissociation constant of acid. It is essentially the Ka, A for acid, K is a constant. So if you're talking about the dissociation constant of a base, it'll be Kb. But for now, like I said, forget about base. Let's focus our talk on acids. So acids, they dissociate. And this dissociation, just like Kw, we said that it is equivalent to hydrogen multiplied by hydroxide, but it's actually divided by water. But because the majority will remain as it is, we just remove it. We consider it close to 1 and it won't make a difference, and we focus on this. So this is not included in the Kw equation. Whereas for acids, no, a big chunk of the acid remains. It only remains as it is, but also a big chunk of the acid does dissociate. So it is significant and we do keep it. So for Ka, it is the hydrogen ion concentration with the base. The base is not OH, it is something else depending on which acid we have, over the concentration of acid in the undissociated phase or stage. This is known as dissociation constant of an acid. Just like from Kw, we were able to come up with the pH equation, and we said it is minus log hydrogen ion concentration. Here we came up with something else. It's called the pKa. pKa is the minus log Ka. Why is this important? Why do we need to know pKa? Because it gives us an idea about feature of a certain acid. Essentially, so just memorize this, know this, and I'll tell you what pKa can tell us in just a second, but I want to show you this representation because I do believe that visual representation helps sometimes convey the message better. So if you have a strong acid and you have a weak acid, remember that weak acids typically only partially ionize. The majority will remain in the undissociated stage. This is just a feature of weak acids. Whereas strong acids, the majority of the acid when in water in an aqueous solution, the majority will dissociate into hydrogen and its conjugate base. So this means that the Ka for this, you'll have the numerator, al-bast, will have a larger number, whereas the denominator is smaller. And when you do the minus log Ka, your pKa value will be smaller, meaning the stronger the acid, the smaller the pKa. Whereas the weaker the acid, because not a lot of this will dissociate, so the numerator المقام بيكون أصغر. فلما تاخذون المقلوب, you take the minus log of that smaller number, you'll end up with a larger pKa. So as a general rule, weak acids have a larger pKa compared to strong acids. That is one thing you need to know. And the other thing that you need to know is that strong acids and strong bases, they typically in an aqueous solution almost dissolve completely or dissociate completely. Therefore their Ka is larger, but pKa is smaller. Whereas the weak acids, they partially ionize into hydrogen and conjugate base. This is the base in this case for acetic acid. And the majority will remain in the undissociated stage. This is why there is two-way arrow that is shown here. Of course, for base, we call it Kb and pKb. We don't say pKa, but we're going to focus our talk on acids. What I want to say here is because the majority will stay here, and this arrow is bidirectional, this makes a mixture of an acid, a weak acid, and its conjugate base ideal for buffering. So if you have this mixture, this buffer, if for whatever reason, somehow you add more hydrogen from outside, you typically will shift the equation in this direction, and this base will pick up, this conjugate base will pick up any excess hydrogen that you added from exogenous sources to make more of this acid, this weak acid. And because it's a weak acid, it will not really have a big impact on pH. So that is why this mixture is perfect for buffers. والعكس صحيح, if you added a base, that base will shift. You don't want there to be alkaline. You don't want the pH to increase. I want to resist that change. I want to keep, for example, the blood the same way it is, or any other environment. I want to buffer it. I want to resist the change in pH. If you add OH, if you add a base from outside, what I'll do, I'll simply dissociate more of this weak acid so I can have more protons, and that will neutralize that effect, and then you'll have water. So you understand the concept of resisting change in pH. That is called buffering. And what is perfect for buffering? It is a mixture of a weak acid and its conjugate base. So back to pH. For buffers, these solutions, these mixtures of weak acid and its conjugate base, we have a separate equation known as the Henderson-Hasselbalch equation. If I give you the H concentration, the hydrogen concentration, by all means, you can simply use the minus log hydrogen ion concentration equation. But in buffers, sometimes we don't have that information. Luckily, for buffers, we have this other equation that you need to memorize. So the pH of a buffer solution, which is composed, قلنا احنا buffer solution عبارة عن weak acid and its conjugate base خليط. So the pH of that solution is the pKa value of that acid, and pKa شيء ثابت ما يتغير. تقدرون تحصلون online. You can find it online, جدول, like a table with all the acids, with all their Ka value and their pKa values. So you don't need to memorize these things. We can give you the pKa value, or we will give you the Ka, for example, value, and you measure pKa. Regardless, this is what the equation is. It's the pKa value of an acid plus the log of the conjugate acid concentration, conjugate base concentration over the undissociated total undissociated weak acid concentration. So this over this, you take the log plus the pKa value, you'll have the pH of the buffer solution. So this is essentially why weak acids make perfect buffers. because they only partially ionize, not like weak, not like strong acids. Strong acids, it'll just completely ionize, but this is only partially, and it's constantly going in both ways. So you still have a lot of the undissociated, which gives us freedom to dissociate more of it if we need it. So if you added excess hydrogen, then what we will do, you shift the reaction to form more of this weak acid, which, because it's weak, it doesn't really change pH that much. It's not going to cause a huge dip or drop in pH. والعكس صحيح. If for whatever reason you added excess base, what you'll do is you'll shift this undissociated acid to form in this direction, to form more of hydrogen that will neutralize your OH. Okay, so it'll shift it in this direction. So it goes both ways, and we can play with this direction to ultimately resist major changes in pH. So that is what buffers essentially are. They are this mixture of acid and its conjugate base. And these buffers resist and minimize changes in pH بشرط أن يكون the pH is around its pKa value, plus minus 1, meaning, I'll show you what that means. And of course, we have different buffering systems in our bodies. There's the bicarb carbonic acid, there's a phosphate, there's a protein, but it is all essentially weak acid or an amino acid and its conjugate base. But what does this mean? It means, if I look at this, I don't want to confuse you, but this is a buffer. This is acetic acid. That acetic acid has a pKa value of 4.8. So as long as, so it has buffering capacity between 3.8 and 5.8, where when you add, for example, OH, hydroxide, a base, or acid from outside, it will resist changes in pH. It will try to keep it in that range, but once it will still change gradually. Once the pH goes outside of its buffering range, of its ability to resist changes in pH, بس خلاص يفقد قدرته على الbuffering. It kind of loses a big it loses its ability to buffer so efficiently. So in other words, الخلاصة, if I tell you what is the مثلا عندكم a buffer solution composed of acetic acid, and you know that the pKa value of acetic acid is 4.8, what is the maximum buffering? At what pH will that buffer work most efficiently? Is it 5, or is it 10, or is it 14, or is it 2? تختارون ال pH اللي أقرب حق ال pKa value. Okay, so this is essentially what it means. You don't need to know details about this graph, so I'll be more than happy to explain it again, but what you need to know is that if you have an acid, a weak acid, this is in this case acetic acid, and its conjugate base, which is acetate, it goes both ways. So you can either shift the reaction in this direction or this direction to ultimately resist changes in pH. معناته أنا إذا ضفت acid من برا, from outside, I'll shift the reaction more towards this way. So this will accept this acid and will form a weaker acid. So it wouldn't change that much the pH. والعكس صحيح. If I added hydroxide, I'll shift the reaction in this direction. I'll form more of the conjugate base and more of the hydrogen, and the hydrogen will form, along with the hydroxide, will form water. So it won't cause a major change in pH, whether you add a base or you add an acid. This is just an exercise of using this equation to measure pH. You can feel free to go through it. If I know you may have a lot of, it may be the concept of ionization of water and the concept of buffers might be new, the Henderson Hasselbalch, and I'll be more than happy to review it with you again. We will definitely review it again next Sunday, but I can also review it tomorrow as well at the beginning of, like, just to give you a recap. For now, I don't want to keep you any longer because I believe I'm over my time and you have a lecture in 1 minute. I do apologize. I promise this won't happen next time. I kind of lost track of time. Thank you.